Our first speakers are Liz Pieri and Jacqueline Pitlars. They are both graduates of the Motion Picture Science program at RIT, so the challenge for you all is to sense the theme in today's session. And they are also both now at Dolby working in the Applied Vision Research Laboratories there. So to talk to us a little bit about emerging color difference metrics in improved visual perception spaces, let's welcome Liz and Jacqueline.
Thank you, David, and hello, everyone. So as David said, we're going to be talking about new color difference metrics for high dynamic range and wide color gamut imagery. Over the past number of years, display and projector manufacturers have been racing to extend their color primaries. We're moving to high dynamic range and wide color gamut, and trends indicate this will continue into the future. We keep having the question asked to us, well, how do I measure color? First, we might want to start by saying, why are they asking this question in the first place? Well, it turns out that they use color measurement to guide design decisions, where if you're designing a monitor and you have this blue primary, and you can say, well, I can't quite reach P3, I have two choices, which one should I make? Knowing how humans see color and how color differences can relate to visual perception can help guide your design decisions in the field. Then there's also calibration. You have it on two fronts. One, if you're a projector or display manufacturer, you might have tolerances throughout your production line. Another one, in a production facility, you might have tolerances to make sure that your mastering display and your production displays are consistent across the line. In the past, for standard dynamic range television, we've had metrics that have worked fairly well. One of them you may have heard of is called ΔICTCP 2000. And the reason we use these metrics is it was independent of the user. So someone could take a device and get a measurement, and they knew that it related to human vision or how they would appear to a human. Unfortunately, as we're moving to high dynamic range and wide color gamut imagery, a lot of those metrics no longer correlate with human perception. So as we move forward in this presentation, our goal is to find that objective color difference metric, such as ΔICTCP 2000, that most closely matches human perception, where the first key is to know how humans see color and find that perceptual color differences for high dynamic range and wide color gamut imagery. And Liz is going to take us through that.
Thanks, Jacqueline. So in order to understand how humans perceive color differences, we need data. And there are a lot of existing data sets, and we have a few examples listed here. We have the McAdam data set, the extended RIT DuPont data set, and the 3M data set. Based off of these sets, we have a generally good understanding of how humans see colors over a relatively limited range, and that was okay for displays in the past, but as technology improves and we move towards high dynamic range displays, a lot remains unknown. So for that reason, we decided to run our own experiment in order to fill in some of those gaps, and that's what I'm going to be talking to you guys about for the next few minutes. So in our experiment, we tested 63 observers, and we used two Christie E3LH laser cinema projectors, and we used the native primaries in order to test as wide of a color gamut as possible. We tested 7 colors, red, green, blue, cyan, magenta, yellow, and white, each at 3 luminance levels of 0.1, 25, and 1,000 candelas per meter squared, or more commonly known as nits. The graph to the right is showing just 1 luminance level for simplicity. We tested white towards the primary colors, and all of the other colors were tested towards white and the adjacent primaries. We also tested a change in luminance for the primaries and for white. Our experiment used a 4 alternate forced choice, or a 4 AFC approach, where there were 3 identical squares and 1 that was different, and the observer's job was to detect the one that looked different to them. Each square spanned 3 degrees of the visual field, and there was a spacing of 0.3 degrees between each. We used a haptic controller design so that observers didn't need to look down and they could keep their eyes on the screen at all times during the experiment while making their choices. The surrounding field is a 1/f noise pattern, which is representative of the statistics in a natural scene, and we made it so that it was equivalent to the test color on average, because we know that when observers are adapted to the color we're testing, they can detect the smallest possible color differences. We showed the noise pattern for 60 seconds at the beginning of each test color. And if you look at the graph on the right, it's showing percentage of adaptation on the y-axis with time on the x-axis. And at 60 seconds, the observer will have adapted to almost 90%. And that means that with an average time of 110 seconds per trial, then by the end of the trial, the observer will have reached a stable state of adaptation. So now we're going to get into the procedure for how we went about determining a just noticeable difference threshold for each observer. First, we had that 60 seconds of adaptation, and then after that, the squares would pop up. And in the beginning, we made it so the difference between the reference and the test colors was very visible. So there was a large difference between the reference and test color. We plotted the distance between those two colors in the UV distance plot in the top right. The observer could then make their selection, and if they got it right, then it would start to get harder. So the difference between the reference color and the test color started to get smaller, which you can see in the graph by the lowering distance. They make their selection again, and if they get it correct, it gets even harder. And now you'll notice the difference is near zero between the reference and test color, to the point where you would expect the observer to not be able to tell a difference, and they might need to guess. If they guess and get it wrong, it would start to get easier again, and the distance between the reference and test color would go up. And that pattern would continue until we converge on a just noticeable difference threshold for that observer, shown by the red dotted line. To drive this point home a little bit, we can think of it in terms of the colors actually being viewed. So we're testing a reference color, which was red, and we were testing towards neutral. So what we wanted to know was how far from the reference color towards the neutral patch we needed to go before the observer could just barely tell the difference between the two. So we took that distance that we measured in U prime V prime, and what that represents is the distance from the reference color, which is the JND threshold. All of this was just for one observer, but you can't really draw conclusions based off of one person, so we had to run this for multiple observers. And this shows the first observer's threshold, and then 13 other observers took the same experiment, and we found thresholds for all of them. And then to get the final data point for our threshold set, we took the average of all of those thresholds, and then the mean, or the error statistic we used was mean absolute error, which is shown by the boxes. That was just for one particular color and test direction, but we also tested across many other colors and test directions, which is what this plot is intended to show. So along the bottom, you see the reference colors and test direction boxes, and the red and neutral boxes correspond to the red towards white example I just showed. So we can take that mean distance that we found and plot it here, and then we did that across all of the other colors and test directions until we had 75 different threshold data points. We segmented the results by luminance, where the darkest colors are all the way to the left and the brightest are on the right. And you'll notice that the distances are higher in the darks because the same perceptual difference in dark colors corresponded to a larger distance in U prime, V prime. And for our data, you can look in our paper, and we have all of that published. So remember that our overall goal was to find the color difference metric that most closely matches human perception. And now that we have data to represent how humans see color, Jacqueline's going to talk about how we analyze some different color difference metrics to see which ones match the most closely with human vision.
Thank you, Liz. First, we need to start out by defining what do we actually mean when we say objective color difference metric. How we're going to define it here is it's a method of color difference measurement that's repeatable and user independent, which means no matter where you are, you can take a device and it will repeat measurements under the same conditions. Some examples is CIE ΔICTCP 94, you may have heard of. Built upon that was CIE ΔICTCP 2000. ΔICTCAM 02 UCS is built on the CCAM 02 model, which is intended to be a color appearance model, which we anticipate to not perform as well here because it's intended for large color differences, but is used in some applications, so we wanted to look at its performance. ΔICTCP is a metric that we created last year, specifically intended for measuring color differences of high dynamic range and wide color gamut colors. So we include it here because we anticipate it to do well. And the last one is the most recently published document, which is the EBU specification. Many of you may have said, this has been done in the past, what are you talking about, it's not new. Well, they recently published a version for high dynamic range and wide color gamut. It happens to have the same color difference metric as it's always had, but it is a recent publication, so we'd like to look at that because it's used frequently for display characterization. As we look at the first results, we're going to start out by looking at just delta E2000 and delta ICTCP. And these two, because delta E2000 is the most commonly used metric in industry, and delta ICTCP because we expect it to perform the best. We'll bring the other metrics in later. This is the same sort of plot that Liz just showed you earlier, where you have that reference color and test direction at the bottom. But here the y-axis is looking at the error of our metrics. So what we did is we took delta E2000 and delta ICTCP, ran it through all our data, and normalized it so that the average was 1. Then we subtracted that 1 so that if it falls on a 0 line, that would mean it was perfectly matching human vision. So anywhere it's above that line is some slight deviations in that metric from the data we gathered, meaning perceptual differences. And we'll start with delta E2000. What we found is somewhat what we expected. We're in those dark regions, so that 0.1 nits you see on the left, delta E2000 does not perform accurately to human perception. It's over-predicting the color differences. And this means that if you're using it for measuring your black level on your display, for example, don't expect that to exactly relate to what you're seeing. Then we can do the same thing plotted with delta ICTCP, and as expected, we saw improvements in that dark region. It's a little difficult to draw conclusions just from this plot, so we've taken the exact same data and analyzed it with other objective metrics, one that many of you are probably familiar with, which is root mean squared error, which essentially will be the deviation from that 0 line. The difference here is the L in RMSLE is log. We took the log error because we care just as much about under predictions as we do about over predictions. And that plot is shown here, and now we've brought in all of our other 3 metrics as well. And we're looking at the delta E series on the left, delta ICTCP, delta camo 2 UCS, and then on the right, the delta LU star V star, that's the EBU grade 1 tolerance specification. And what we find with RMSLE is that delta ICTCP is the best performing metric, because here a low number is a better performing metric. Now, you might say, okay, fine, but we saw how badly delta E did in those dark regions. Maybe that's skewing your results. Maybe we could just use delta E2000 for bright colors. We thought about that too, so we got rid of these results and reran the analysis to see how it would perform on colors that it was designed for. And this is the plot without that data. So what we find is, even still, we find that delta ICTCP, given RMSLE analysis, was the best performing metric, or the most accurate to human perception. We do find that here, camo 2 UCS doesn't perform as well as some of the delta E metrics. Again, it's meant for larger color differences, not extraordinarily surprising. And we find that the EBU tolerance is roughly on par with the delta E series. RMSLE may not be the best metric to use for analyzing these color differences, so we looked at some other ones too to get a more well-rounded data set. 2 that are commonly used in color difference metric analysis. The first one is PF/3, or performance factor, and this is a combined index. So they've taken different measurements that have been used over the years and combined it to a single number, which is roughly the percentage of error in all of these different pairs. Then also the stress, or standardized residual sum of the squares, which is a loss function, and it can be used to determine significance. The reason we use this is many have said it's an improvement to outliers, and so it's starting to become common in color difference measurement analysis. We can plot the exact same thing we did before using all those metrics. RMSLE is on the left side of that plot, and then PF/3 and stress. And what you find is, given all of those metrics, delta ICTCP is still the best performing metric. Those numbers are interesting, but what does that actually mean to you in a practical sense. So here we'll look at a plot of what it would actually mean if you were designing a monitor or if you were designing a calibration tolerance. So we take, as an example, the blue point, and we look at delta E2000, for example. We say, what would delta E2000 tell us is a perceptual difference in the green? And we plot that. And we say, okay, well, what would delta E2000 tell us is a perceptual difference towards white and towards red? And we can keep going around all the way in a circle, and this is showing everything inside that delta E2000 circle is supposed to be perceptually equivalent to that blue color in the very center. So this is delta E telling us what a just noticeable difference is. We can take this exact same plot and now plot the perceptual differences that Liz talked about earlier to see how well it correlates with what delta E is saying. And that's what we're showing here with those black lines, where those gray circles are our mean absolute error. What we find is that in some cases, it doesn't correlate perceptually. So take the blue towards red, for example. It's much shorter than delta E2000 predicts. It's a little counterintuitive, but because it's shorter, that means delta E2000 is under predicting the color difference, versus blue towards green, delta E2000 is over predicting the color difference. And what this means practically is that sometimes if your primaries are a little bit red or a little bit green, delta E2000 is going to give you very different answers, even though it might appear exactly the same to you. A perfect perceptual metric, meaning one that correlates well with human vision, would follow along these results perfectly. There's many different ellipse shapes you can make with this, so we're not drawing conclusions about the exact shape. All we're looking for is that they should at least go straight through those circular lines. Then if we do the exact same thing with delta ICTCP, that's shown in cyan up there. So we see a much greater correlation in this color. We'll look at more colors in a little bit to our perceptual data. We can do the same exact thing now. We'll look at the EBU tolerance. And that's what's plotted here. So EBU is specified, as I said, in U star V star, which is also circular in U prime V prime. So what that means is those tolerances are always going to be circular. So anywhere I'm showing you results where that perceptual data doesn't seem like it would fit a circular shape, that means that the EBU tolerance may not be the best way of characterizing a display, because slight changes in primary could give you very different results perceptually. The other thing, just as a note, is that this is the actual size of the EBU grade tolerance. So just be aware that when you're following the grade 1 tolerance, that doesn't mean that you won't see a difference in colors, because it is larger than a just noticeable difference. So we'll start by looking at 3 colors at the 25 nit range. On the left, I wanted to start out with an example where delta ICTCP does not perform as well, because we're not coming here and saying, oh, it's the absolute perfect solution to everything. This is an example. It happens to be the only example in our test data where delta ICTCP does not perform as well. You see delta E2000 with that magenta circle correlates much better with those points. I will point out that delta ICTCP is Euclidean distance, roughly, in ICTCP. So there's definitely room for improvement, but as a metric, overall, it performs significantly better than the most commonly used metric today. That blue point in the very center is the exact same that we looked at previously. I want to take it from a display manufacturing side. If you were designing a display, what would this mean to you? It means that if you were choosing that P3 blue, like I was talking about before, and you had a choice between P3 blue going a little red or going a bit green, and you use delta E2000 to tell you what to design, it's going to tell you that you can go way red. So red that an actual P3 display would look completely different to you. And if you were to do your blue primary a little bit green, it would say, oh, it's totally fine, but visually you might say, okay, it doesn't work out. So just be cautious if you're using delta E2000 as your measurement, and perhaps start using other measurement metrics as well. Then on the right side is the biggest deviation in delta E2000. So that long ellipse that it creates, a lot of it's chopped off on the sides, is the biggest deviation that ΔT2000 has, where that red towards green versus the red towards blue will give you completely different answers. This can be a challenge in calibration because that means that if you're calibrating red towards green, you could be calibrating for hours and it would still say, no, it's not good enough, no, it's not good enough, even though you wouldn't be able to tell a difference in the first place. So this can be a little balance of trade-off of efficiency that can be caused by using a metric that's inaccurate to human perception. The last thing we're going to look at here is the results of the neutral colors at various luminance levels. We're looking here at white at 0.1 nits, at 25 nits, and 760 nits. The reason this is 760 here is because when we were testing towards blue, it had to be lower because the luminance of blue is quite low. So when we're looking at this, what we find is that it mimics the results we saw in that line plot earlier. Where at 25 and 760 nits, ΔICTCP and ΔT2000 follow roughly a similar size, where ΔTE2000s may be a little small, ΔICTCP may be a little bit big, but as we go to that 0.1 nit case is where we find ΔTE2000 starting to break down a bit, where ΔTE2000 stays the same size as it had been for the 25 nit and for the 760 nit case, because it hasn't been designed to go to those low luminance colors. So ΔICTCP, because it was based on a lot of the results created last year that included some of these colors, scales with the human perceptual differences in those low luminance colors.
So to sum everything up a little bit, at the beginning we mentioned that color differences, perceptual color differences are important to use when guiding design decisions and also for calibration purposes as well as setting tolerances. But the problem was that perceptual color difference data didn't cover the full HDR range and there were a lot of points missing. And that's why we decided to complete our own threshold experiment where we tested colors at 0.1, 25, and 1,000 nits with near Rec 2100 primaries. And the point of all that was to build up a data set that would tell us how humans see colors for high dynamic range and wide color gamut colors.
Then we took that data and we used it to compare leading color difference metrics, such as the ΔE series, Camo2 UCS, ΔICTCP, and the EBU grade 1 specification. And we compared that data first, looking at ΔT2000 versus ΔICTCP in that line plot. Then we analyzed some objective metrics. And then finally, we compared how it would affect practical applications through those ellipse plots. After all of this, what we find is that ΔT2000 was unreliable for those dark colors and had large perceptual deviations for the same color in different directions. We found that the EBU specification was much larger than a just noticeable difference and also had its own slight perceptual deviations at the same color in different directions. We found that ΔICTCP was the most stable and closest performing metric to human thresholds of color differences. So in the end, we found that ΔICTCP should be used as a measure of perceptual color differences for HDR wide color gamut imagery, especially as it relates to guiding design decisions and use in calibration and calibration tolerances. Thank you.
Do we have any questions from the audience? Anyone like to raise a concern? Come up to the microphone, please, in the center.
Good presentation. One question is that the colors used were seemingly very, very saturated, close to Rec 2020, which in most normal imagery don't exist. And I wonder if we're basing the study on these really outlier colors versus more normal colors, say like P3 or something where most normal imagery exists, what the differences would be. Because it seems like that would be a more practical use, is we'd be more concerned about colors we actually use. And also some of these outlier colors may have a greater differential across different observers too as we get way out there?
That's a great question. So first about the different observers, that is true, but we did not see a large deviation from one person to multiple people, which is showing us that metamerism wasn't as large of an effect as we expected. Going back to, yes, these are outlier colors. We were specifically testing the bounds. You can look at neutrals for a little bit of guidance, but the reason we didn't include those is because, as Liz stated earlier, there's a lot of data out there that already exists, and there's no need to reinvent the wheel. So the presentation we gave last year and how Delta ICTCP was designed was based on that data that already exists. So that's why we didn't repeat the experiment with that data.
Well, one thing that I don't think exists well is like on certain memory colors, like skin tones and things, across a wide dynamic range. I mean, it seems like that would be interesting. I think the standard data sets that are available now are in the more limited SDR range. So, and those are certainly, when you're calibrating anything, you know, those memory colors have to be, you know, get the first attention.
I completely agree, and that is a great point. It's just a matter of time, so that could be a next step. We wanted to start with the limits and go from there.
Thank you.
Gerlinger, IoT Munich. One question about which technique do you make this research? With plasma technique, with LCD displays, or what was the technique behind this?
Mm-hmm. So you're asking what display the experiment
Yeah.
was done on? Okay. Do you want to say?
Yeah, we used 2 laser cinema projectors. So, yeah.
So in this case, the primaries are really small bandwidth.
Yeah.
Okay. And the metamerism were how much?
What was that?
The metamerism out of this, the differences between certain viewer. How much?
So as I said, the previous question kind of asked that as well. So how we analyzed that to start out with was, what is the deviation between one observer repeating the
Okay.
experiment versus the population? And we found that the results were fairly similar, given you expect a population to be bigger. So I was very surprised that metamerism didn't seem to be a large effect on color differences. Whether that color actually appeared the same or not, that's a different story we didn't look into, but color differences seem to be measured similarly between observers.
Okay, thank you.
What is the relationship between delta ICTCP and ICTCP?
The CT axis is divided by 2, and then it's Euclidean distance.
Okay.
The reason for that was because when we designed ICTCP as an encoding space, you want to use all the space you have in order for bit depth to be used most efficiently. So we took a perceptual metric of ICTCP and doubled the CT axis so that we use all the bits. And now that we're talking about perception again, divide it by 2, and then it's Euclidean distance.